The slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. It does not have ownership. It does not have ownership. Here's a small programming problem. Write a function that takes a string of words separated by spaces. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in the string. If the function doesn't find the space in the string, the whole string must be one word, so the entire string should be returned. Let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. Let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. Oh, wait a second. Without using slices. First word. The first word function has a string, ampersand string as a parameter reference. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word. Indicated by a space. Let's try that, as shown in listing 4-7. The first word function that returns a byte index value into the string parameter. Bytes as bytes as a byte. Bytes iter enumerate. Because we need to go through the string element by element and check whether a value is a space. Because we need to go through the string element by element and check whether a value is a space. We will convert our string to an array of bytes using the asBytes method. Next, we create an iterator over the array of bytes using the iter method. Next, we create an iterator. We create an iterator over the array of bytes using the iter method. Here. We will discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection and that enumerate wraps the result enumerate wraps the result of iter and returns each element as a part of a tuple instead. The first element of the tuple returned from enumerate is the index. And the second element is a reference to the element. Second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. This is a bit more convenient than calculating the index ourselves. This is a bit more convenient than calculating the index ourselves. Yeah. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. Because the enumerate method returns a tuple. Because the enumerate method returns a tuple, yeah. We can use patterns to destructure the tuple. We will be discussing patterns more in chapter 6 in the for loop. We specify a pattern that has I. In the for loop, we specify a pattern that has I for the index in the tuple and ampersand item for the single byte in the tuple. And ampersand item for the single byte in the tuple. Okay. We specify pattern design for the index because we get a reference to the element. We get a reference to the element from iter enumerate. We use ampersand in the pattern. We get a reference to the element. We get a reference to the element. We get a reference to the element. So enumerate return the reference to element. Okay, that makes sense. Inside the for loop, we search for the byte that represents the space by using the byte return syntax. Okay. Inside the for loop, we search for the byte that represents the space by using the byte return syntax. If we find the space, we return the position. Otherwise, we return the length of the string by using slen. We now have a way to find out the index of the end of the first word in the string. Of the end of the first word in the string. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We are returning a use size. We are returning a use size on its own, but it's only a meaningful number in the context of a string, ampersand string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 4-8 that uses the first word function from listing 4-7. 4-8 storing the result from calling the first word function and then changing the string contents. Word will get the value 5. Yeah, 0, 1, 2, 3, 4, 5. This empties the string, making it equal to, okay. Word still has the value 5 here. But there's no more string that we could meaningfully use the value 5 with. Word is now totally invalid. That makes sense. Okay, that makes sense. This program compiles without any errors and would also do so if we use the word after calling s.clear. So this program compiles without any errors. This program compiles without any errors. This program compiles without any errors and would also do so if we use the word after calling s.clear. Because the word isn't connected to the state of s-error, word still contains the value 5. Yeah, because it's totally separate value. We could use that value 5 with the variable s to try to extract the first word out. But this would be a bug because the contents of S have changed since we saved the 5 in Word. Having to worry about the index in Word getting out of sync with the data in S is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Usage. Now we are tracking a starting and an ending index. Now we are tracking a starting and an ending index. And we have even more values that were calculated from data in the particular state but aren't tied to that state error. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem, string slices. So this is a problem too. But aren't tied to the state at all. We have 3 unrelated variables. Yeah, they are unrelated. Yes, that makes sense. Luckily, Rust has a solution to the problem, string slices. String slices here. String slice here. String slice here. String slice here. String slice is a reference to a part of a string, and it looks like this. Okay, this is okay. Slice here. So rather than a reference to the entire string, here is a reference to a portion of the string specified in the extra 0 to 5 bit. We create slices using a range. We create slices using a range within brackets by specifying starting index, ending index. Where starting index is the first position in the slice and ending index is one more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So in the case of let world, 6 to 11 world would be a slice that contains a pointer to the byte at index 6 of S with the length value of 5. Wait a second. Internally, the slice data structure internally data structure internally the data structure store the starting point. Internally, slice data structure stores the starting position and the length of the slice. Slice. Okay, so starting point, starting position, and the length of the slice. Which corresponds to ending index minus starting index. Starting index, okay, makes sense. So in the case of let world, world would be a slice that contains a pointer to the byte at index 6 of S with the length value 5. With the length value of 5. That makes sense. Okay. With Rust's range syntax, if you wanna start at index 0, you can drop the value before the two periods. In other words, these are equal. You can drop the value before the two periods. You wanna start in index 0, okay, makes sense. By the same token, if your slice includes the last byte of the string, by the same token, if your slice includes the last byte of string, you can drop the trailing number. That means these are equal. Oh, and okay, that makes sense. Oh, you can also drop both values to take a slice of the entire string, so these are equal. You can also drop both values. You can also drop both values to take a slice. Okay, makes sense. Okay. Note: string slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of the multi-byte multi-byte character, string slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multiple byte character, your program will exit with an error. For the purposes of introducing using slices, we are assuming ASCII only in this section. A more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. If you attempt to create a string slice in the middle of a multi-byte character, which only should be at the valid UTF-8 boundaries. Okay. With all this information in mind, let's rewrite the first word to return a slice. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as $str. So this means that I'm going to return the string slice as bytes. Bytes iter enumerate, and then doing this, and then this means I'm returning the okay, this makes sense. Okay. Okay. And percent this. We get the index for the end of the word. We get the index for the end of the word. We get the index of the end of the word. Okay, makes sense. In the same way as we did in listening for the 7 by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Return a string slice using the start of the string slice. And the index of the space. And this index of the space as the starting ending indices. Yeah, makes sense. Now when we call first word, we get back a single we get back a single value that is tied to the underlying data. Oh, because the reference. Yeah, it's because the reference. Yeah, okay, that makes sense. If you attempt to, oh wait, it's not there. Type in the line data, the value is made up of a reference to the starting point of the slice and the number of elements in the slice. The value is made up of a reference. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. And number of elements and the value is made up of a reference to the starting point of the slice and number of elements in the slice. Yes, this one. Okay. Returning a slice would also work for a second word function. Returning a slice would also work for a second word function. Returning a slice would also work for a second word function. We now have a straightforward API that's much harder to mess up, because the compiler will ensure the references into the string remain valid. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word, but then cleared the string so our index was invalid? That code was logically incorrect, but didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an empty string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the sliced version of the first word, it will throw a compile time error. Immutable borrow occurs here. Error. Immutable borrow occurs here. Immutable borrow later used here. Immutable borrow. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Because clear needs to truncate the string, it needs to get a mutable reference. The println after the call to clear uses the reference in word. The println after the call macro after the call to clear uses the reference in word. So the immutable reference must still be active at the point. So the immutable reference must still be active at the point. Oh, so immutable borrow occurs here, and then immutable borrow occurs here. Then I use it here. Yeah, it should be immutable, like but it's quite already immutable. Yeah, makes sense. Um, Rust disallows the immutable reference in clear and the immutable reference in word from existing at the same time, and compilation fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. String litters or slices. Recall that we talked about string litters being stored inside the binary. Now that we know about slices, we can properly understand the string litters. Recall that we talked about string litters being stored inside the binary. Uh, now that we know, now that we know about slices, we can properly understand string litters. The type of S here is $str is a slice pointing to the specific point of the binary. This is also why string litters are immutable. $str is an immutable reference. Oh, because this string litter is slice and slice as an immutable reference to the string. Okay, that makes sense. String slices as parameters. Knowing that you can take slices of returns, knowing that you can take slices of returns and string values leads us to one more improvement on first word. String slices as parameters. Okay. Knowing that you can take slices of returns, knowing that you can take slices of returns can take slices of letters and string values leads us to one more improvement on first word, and that's its signature. A more experienced Rustacean would write the signature shown in listing 4-9 instead because it allows us to use the same function on both string values and str values. Hmm. First word function by using a string slice for the type of the parameter. If we have a string slice, we can pass it directly. If we have a string, we can pass a slice of a string or a reference to the string. The flexibility takes advantages of deref recursions. A feature we will cover in the implicit deref recursion with the functions and methods section of chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Defining a function to take a string slice. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Um, okay. First word works on slices of strings, whether a partial or whole. First word works on slices. First word works on slices, of strings, whether partial or whole, makes sense. The first word also works on a reference to strings, which are equivalent to whole slices of string. My string liter. Uh, First word works on slices as of string letters. Or slices of string letters with a partial rule and ampersand. Because string letters are string slices already, this works too without the slice syntax. My string literal. Okay, my string literal. Percent density. And percent my string literal. My string literal. 6 strings. Kind of makes sense. This is a value, and then it's a reference. Immutable reference. Kind of makes sense. Yeah, that makes sense. Other slices, string slices that you might imagine are specific to strings, but they are more general slices type. To consider this array, string slices that you might imagine are specific to strings. There's a more general slice type too. Just as we might want to refer to part of a string, we might want to refer to part of an array. We do so like this. Array ampersand array. So this is a part of this, and then reference. So it's just slice, and then slice, and then 2, 3, and then ampersand. That makes sense. Ampersand 2, 3 is basically what 2, 3 is. The slice has the type ampersand I32. The slice type is ampersand I32. Okay. It works the same way as a string slice do, by storing a reference to the first element and length. You will use this kind of slice for all sorts of other collections. What? Emit. The slice type, it works the same as a string slices do. It has the slice as the type and percent I32. It works the same way as the string slices do by storing a reference to the first element and an length. You will use this kind of slice for all sorts of other collections. We will discuss these collections in detail when we talk about vectors in chapter 8. Consider the variable s2 and s3 in following program. These two variables will be located in memory. These two variables will be located in memory within the stack frame for main. Each variable has a size in memory on the stack. For not including the size of pointed data. Which statement is true about the sizes of S2 and S3? Which statement is true about the sizes of S2 and S3? S3 has more bytes than S2. String from hello S string %, this string and %s. S3 has the fewer bytes than S2. Determine whether the program will pass the compiler. String S has bytes iter item. Percent item. Item BL Failure. Item equals to BL byte L and push str world s. This will compile for sure. Hello. This will not compile. This will compile. Mute. Item. Um, Hello. Does it work? Mm, Hello. Hello. Hello world. Uh, Keyword. I don't know. Shit. This 3 is a pure bytes. This is more bytes. Oh, with 3 is more bytes than 2. What is string from hello 9% the string 9% this um the time and percent string is a normal reference consisting of a single pointer. So it bytes on a 64-bit architecture. The type SC and SCR is a special slice reference which consists of a pointer and a length. Oh, reference point. Okay, makes sense. Makes sense. Makes sense. This program compiler offers line number 5. Because S as bytes, it produces an immutable reference to S. Oh, immutable reference to S, right? Select mutate inside of OBS, that makes sense. Summary: the concepts of ownership, borrowing, the slices ensure memory safety in Windows programs at compile time. The Rust languages gives you control over your memory usage in the same way as the other system programming languages, but having the owner of data automatically, but having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work. So we will talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping pieces of data together in a struct. Uh, some other okay.